formula for a voltage drop across an inductor is given by the formula V equals L di dt. One way of thinking about this is that inductors oppose changes in current. The larger the change in current, the more rapidly current is changing, the more voltage needs to be applied across the inductor. This means that if you take an inductor, connect it to a circuit, and then suddenly change that circuit, the current in the inductor after the sudden change will be equal to the current in the inductor just before the sudden change. On the other hand, once an inductor has reached its steady state condition, the current will be constant, which means di dt is zero. After a long period of time, an inductor will allow a current through it and will have no voltage across it. Both of these properties are the opposite of how they were for capacitors. Remember, for a capacitor, it keeps the same voltage it had before, and after a long period of time, it has no current. For an inductor, it keeps the same current it had before, and after a long period of time, it has no voltage. Now, despite being nominally the opposite of a capacitor, an inductor still behaves a lot like a capacitor when placed in a circuit with resistors. In particular, we can still use the time constant equation, x of t is equal to x of naught times e to the negative t over tau, or x of t is equal to final x times 1 minus e to the negative t over tau. Recall, this equation is used for some value that starts at zero, or starts at a maximal value and then drops down to zero over time. And this is for a value that starts at zero and rises up to some maximum value over time. The difference between an inductor and a capacitor is that the time constant. Recall that for a capacitor, the time constant was R times C. For an inductor, the time constant is now L divided by R.